All right, we're going to look at another problem to do some curve sketching here. This time we have it's going to be a fourth degree polynomial if we FOIL that all out. When it's factored out, I can easily see what the intercepts are. X squared plus 4 has intercepts of plus and minus 2i, but we're not going to graph on the complex plane. It's just going to be real numbers. So we have x-intercepts at 1 and negative 3 from those two factors. So 1, 0, and negative 3, 0. If we plug in 0 in for the x, we're going to have 4 times negative 1 times 3, and that's going to give us a y-intercept of negative 12. Okay, so there's our intercepts. What we're going to do now is we're going to go through and FOIL it out. It's probably going to be a little bit easier to take the derivative if we go ahead and expand that out. Okay, so just routine foiling and expanding it out. So keep multiplying it through, and then we'll combine our like terms, and then what we'll do is we'll take the first derivative and set that equal to 0 to find our critical numbers. So there's this is a polynomial, it's nice and smooth, so there's going to be no places where it's not going to be differentiable. Okay, so our regular function is x to the fourth plus 2x cubed plus x squared plus 8x minus 12. And then we'll use the power rule to take the derivative of that. So we have 4x cubed plus 6x squared plus 2x and plus 8. And so there's some things that we can do. If you're working on a problem out of the textbook, chances are you'll be able to do something like factor by grouping. Worst case scenario, you'd use the rational roots theorem, the PQ stuff, and the synthetic division to break down the polynomial. However, since I just made up this problem and I wanted to have certain properties, it doesn't work out real well. So what I did to set the derivative equal to set the derivative equal to 0 and then solve it. It's kind of hard to do with a cubic, so you can use like your graphing program on your calculator and find where the intercept is by graphing this. I just used Wolfram Alpha, and so it gave me a critical number where the first derivative is equal to 0 at approximately negative 1.8. From there, what I would like to do is I'd like to test on either side of negative 1.8 to look for increasing, decreasing type of behavior. So that's what we're going to do here. So I'm just going to write our derivative here. And we're going to test around negative 1.8. So f prime of negative 2. I wanted to make sure I was plenty away from negative 1.8 because I did round it. Negative 2 seemed reasonably far away enough. If you want to be extra careful, you can do something like negative 5. And that gave me a negative for the first derivative, which tells me that the function's decreasing. Then I plugged in something like 0, and we know what that is. That's 8, so that's easy to see, so that's increasing. So I went from decreasing to increasing, so the first derivative test tells us that that's going to be a minimum. Now to find the y value that goes along with that, I have to go back to the original function and plug in negative 1.8, and I got about negative 24.3. And that's going to be my minimum of the function here. Okay. Alright, now we're going to go ahead and take the second derivative of our polynomial, and we're going to look at concavity. So we get 12x squared plus 12x plus 2. And again, a lot of times if you're doing one out of the textbook, they spend a lot of time making sure that everything worked out nicely. It's going to factor. So this one's not going to factor, so I use the quadratic formula. So I'm not going to go through the details of the quadratic formula, but I got two values. X is approximately negative 0.8 and negative 0.2. So we got a test around there, and we're looking for either positive or negative in terms of concavity. Now, we shouldn't have to think too hard about this. This is a parabola. It's opening up, and it's got x-intercepts like this. So you have positive here, which tells us concave up, and then down in this portion it's negative, so that's going to give us the concave down. Of course, we can test that in some numbers in the second derivative, and it will come up with the same results there. Okay, now what I need to do is the negative 0.08 and negative 0.2. You see how they both have a change in concavity from happy face to sad face, and then from sad face to happy face. So we have points of inflection at negative 0.8 and negative 0.2. Oops, looks like I erased the P there. Okay, and what I need to do is plug in negative 0.8 and negative 0.2 back into the original function to find the y values. Okay, so we're going to do that. Okay, well, those are my original y values. Now, one thing that I didn't do that I've done in the other curve sketching videos is I checked for concavity. I mean, not concavity, even, odd, or neither. But this is a mixture of exponents. It's got an x to the fourth. It's got an x cubed. So if I have an even and odd, then it's not going to be either even or odd function. So I didn't even bother to do that. Okay, so we're about ready to put everything in. So we're just going to write our function over here. F of x is equal to x squared plus 4 times x minus 1. Oops, we have the square in the wrong location. Where will we fix that? That's not where the square went. Right there on top of the x. Okay, now that's better. Okay, x squared plus 4, x minus 1, x plus 3. And because I know my mins and maxes and all that kind of stuff, I'm going to choose my scale appropriately. So on the y-axis, I need to get all the way down to negative 24.3. I don't need to go too far on the x-axis. So there, at negative 3, at 1, and then at negative 12, those are our two x-intercepts and our y-intercept respectively. We can go ahead and put in our minimum way down there at negative 1.8 and negative 24.3. And then also we can put in our points of inflection. So we got a point of inflection here and here. Now, when we did the first derivative, we have on this side we are increasing. On the other side of our minimum we were decreasing. Okay, and we have our point of inflection here and here. In between we had concave down, and then outside of that is concave up and concave up. So we're going to put that stuff in a little bit nicer though. About as nice as you can on the iPad. Alright, so increasing, decreasing on those sides. There's your concave down portion, concave up, and concave up all the way out. Okay. So if it's kind of hard to see, it's probably the artist's fault on this one. Okay. And there is our graph of our parabola with about everything that we could want from it in terms of intercepts, mins, maxes, points of inflection, intervals increasing, decreasing, intervals of concave up, concave now. The only thing to make it any more accurate than what it is to plot more points.